A spacecraft leaves Earth. The engines are perfect. The shielding holds. The crew is trained beyond anything humanity has ever produced. And yet somewhere out there in the black, past a point no map has ever marked, that mission ends. Not because the ship breaks apart, not because space suddenly becomes a wall, but because the distance itself has quietly turned into something no human body was ever built to carry. Time, radiation, silence, aging metal, aging bones, a rescue call that will not arrive for years, maybe decades. Tonight we investigate the invisible line where space stops being merely difficult and becomes fundamentally impossible for a single human crew to cross alive. The human survival horizon, where distance stops being measured in kilometers and starts being measured in lifetimes. If space, and the strange edges of what it actually means to be human out there in it, is the kind of thing you enjoy thinking about, a like and a subscribe genuinely helps this channel keep making these. Now, are you comfortable? Let's begin. Imagine, for a moment, a single spacecraft leaving Earth. It does not matter for now what it is made of, or who is inside it, or where exactly it is going. What matters is that it is moving outward, away from the atmosphere, away from the blue curve of the horizon, away from the network of ground stations and rescue helicopters and hospitals and every other layer of quiet, invisible support that has kept every human being who has ever lived alive. The spacecraft continues, past the International Space Station, past the orbit of the Moon, past Mars, past Jupiter, past everything. And here is the question that this entire episode is going to try, honestly, to answer. Is there a distance out there in the black, somewhere along that outward path, past which no human being can survive the journey? Not because the ship fails, not because the mission is badly planned, but because distance itself has become fundamentally incompatible with staying alive. The intuitive answer feels like it should be yes. Somewhere out there, surely, is a line, a coordinate, a boundary in space where a human being who crosses it does not come back. But if you sit with the physics for even a few minutes, that idea falls apart. Space contains no wall. There is no invisible boundary in the vacuum where atoms stop working or biology quietly ceases to function. A human body floating 100 kilometers above Earth and a human body floating 100 billion kilometers away from Earth are, at the level of chemistry, doing exactly the same thing. Space itself does not care where you are, and yet, the answer to the question is still, in a real and unsettling way, yes. There is a distance no one can survive. It is just not the kind of distance you might think it is. Because the real enemy out there is not physical space. The real enemy is what physical space creates. And what it creates, more than anything else, is time. Every extra kilometer between a spacecraft and Earth is another kilometer that a rescue mission would have to cover. Another second of communication delay. Another minute of exposure to charged particles that Earth's magnetic field is no longer holding back. Another day that the recycling system has to keep working without a replacement part. Another month of muscle and bone quietly wasting away under the wrong gravity. Distance in space is not really a length. It is a duration. It is a slow, cumulative pressure that builds on a crew and on their spacecraft until something somewhere in the long chain of biology, chemistry, engineering, and psychology gives way. That is what this story is really about. Something more subtle and honestly more frightening. A moving threshold that we are going to call, for the purposes of this story, the human survival horizon. The human survival horizon is not a fixed line drawn on a star chart. It is a practical limit that shifts depending on how fast a spacecraft can travel, how well it can shield its crew, how much food and water and oxygen and medicine and spare parts it can carry, how reliably its life support can recycle what it has, and how long the human beings inside it can endure being cut off from the world that made them. Change any one of those variables, and the horizon moves. Push the ship faster, and the horizon moves outward. Shrink the medical bay, and it snaps back in. The same destination can sit safely inside the horizon under one mission design, and hopelessly beyond it under another. Mars in 6 months is a hard mission. Mars in 6 years is a different problem entirely. A journey of 100 years is not the same kind of thing as a journey of 100 days, even to the same star. The distance has not changed. The time has. And time, unlike distance, is something the human body cannot ignore. So let us begin where every real journey has to begin. Close to home. Because to understand where the horizon eventually becomes uncrossable, we first have to look at where it is still forgiving. We have to look at the places we have already been. The first and gentlest calibration point is low Earth orbit. The International Space Station orbits at an altitude of roughly 400 kilometers above the surface. That sounds like a large number until you compare it to almost anything else in space. The Moon is about 1,000 times farther. Mars, at its closest, is over 100,000 times farther. In the grand geometry of the solar system, the space station is essentially still touching Earth's face. That closeness is not a detail. It is the entire reason the space station works as a human habitat. When something goes wrong on board, and things do go wrong constantly, in ways that rarely make the news, Earth is right there. A Soyuz or Crew Dragon capsule attached to the station can, in principle, undock and return crew to the surface in a matter of hours. When an astronaut has a medical concern, they can speak in real time with flight surgeons on the ground. There is no meaningful delay. The conversation is a normal conversation. Communication travels at the speed of light, which sounds like an abstract physics fact until you realize what it means at these distances. From 400 kilometers up, radio signals reach the ground in a little over 1 millisecond. For every practical purpose, an astronaut on the space station is in the same room as mission control, and there is one more layer of protection at this altitude that is easy to forget. The space station is still inside Earth's magnetic field. Not deeply inside it, but inside it. That field is the reason the surface of Earth is habitable at all. It deflects the majority of charged particles streaming outward from the sun, the solar wind. And it also blunts the impact of higher energy cosmic rays from farther out in the galaxy. Astronauts on the station still receive more radiation than people on the ground, roughly comparable over the course of a 6-month stay to that experienced by workers in certain terrestrial industries over years. It is not nothing, but it is manageable. It is a dose, not a catastrophe. Low Earth orbit, in other words, is not really deep space. It is a very high place. A hostile one, absolutely, but one where every layer of protection that keeps a human alive on Earth still, in some diminished form, applies. Rescue is measured in hours. Communication is measured in milliseconds. If something breaks, it can be replaced. If someone is hurt, they can come home. Now let us move the spacecraft outward. Not to another star. Not even to another planet. Just to the Moon. The moon sits on average about 384,000 kilometers from Earth. It is by far the farthest any human being has ever traveled. 24 astronauts over the course of the Apollo program made that trip. 12 of them walked on the surface. The last of them, on Apollo 17, left the lunar surface in December of 1972. In more than 50 years since, no human being has been that far from home again. At the moon's distance, communication is still fast, but no longer instantaneous in any felt sense. A radio signal takes about 1.25 seconds to reach the moon from Earth, and another 1.25 seconds to come back. Total round trip, about 2.5 seconds. If you have ever been on a satellite phone call or a badly lagged video conference, you know what this feels like. It is a conversation, but a conversation with a small, persistent gap. You can still talk. You can still coordinate. You can still be talked through an emergency step by step in something close to real time. It works. Travel time is longer, of course. Apollo missions took roughly 3 days to reach the moon. Not 30 seconds, not 3 hours, 3 days. That number matters because it introduces something new into the story. The reality that once a crew is out there, they are out there for a while. Any rescue would take at least that long to reach them. Nobody is grabbing a Soyuz and being on the lunar surface in an afternoon. And there is Apollo 13. If you know one story from the space age, it is probably this one. In April of 1970, an oxygen tank on the service module of Apollo 13 ruptured on the way to the moon. The command module was crippled. Landing was immediately impossible. The 3 astronauts on board, James Lovell, Jack Swigert, and Fred Hayes, were nearly 250,000 miles from Earth, in a vehicle now leaking air and losing power, and they had to find a way home. The reason they made it back is worth pausing on. It was not luck. It was not one clever engineer at a chalkboard. It was the fact that they were still, by every meaningful measure, close. Close enough that Mission Control could talk to them in near real time. Close enough that the trajectory back to Earth, using a lunar gravitational slingshot, took only a handful of days. Close enough that the ship's remaining supplies, stretched to their absolute limits, could just barely last the return. Close enough that when Apollo 13 finally splashed down in the Pacific Ocean on April 17th of 1970, the entire ordeal had lasted less than a week from the moment the tank exploded. Now, imagine that same failure occurring not near the moon, but on the way to Mars. This is where the story shifts in a way that most people do not fully appreciate until they see the numbers laid out honestly. Because Mars is not just a slightly farther moon. Mars, from the point of view of a human crew, is a different category of destination entirely. It is the first place in the solar system where the entire architecture of rescue quietly collapses. Start with distance. Mars and Earth do not sit at fixed distances from each other, because both planets are orbiting the Sun on different tracks at different speeds. The closest they ever come to each other is roughly 55 million kilometers. The farthest they get from each other when they are on opposite sides of the Sun is over 400 million kilometers. That is a range spanning roughly a factor of 7 or 8, and a crewed mission does not get to pick which of those numbers applies. The mission's timing is chosen by planetary geometry, not by the crew's convenience. Now translate that into communication delay. Even at the closest approach, a radio signal between Earth and Mars takes about 3 minutes to travel one way. Round trip, about 6 minutes. At maximum distance, one-way delay stretches to over 22 minutes. Round trip, close to 45 minutes. Sit with that number for a second. 45 minutes. That is the round trip time for a single question and a single answer, at the worst case. If a crew member on Mars has an emergency and calls Earth for guidance, the message takes over 20 minutes to reach the flight surgeon. The flight surgeon takes some time to think, perhaps consult a colleague, perhaps look at data. Then the reply is sent, and it takes another 22 minutes to arrive back at Mars. By the time the answer reaches the patient, the situation is not what it was when the question was asked. It cannot be. Too much time has passed. Real-time medical guidance, in the way we experienced it on the space station or even at the moon, does not exist here. Mission Control cannot talk a Mars crew through a cardiac emergency, the way it once talked Apollo 13 through a course correction. The physics of light itself forbids it. Even if every ground controller was a doctor and every astronaut a patient, the conversation would arrive too late. Now add the second problem: launch windows. Because Earth and Mars are moving on separate orbits, there are only certain periods of time when it is energy efficient to launch a spacecraft from one to the other. These are called launch windows, and they open roughly once every 26 months. Miss one, and you wait more than 2 years for the next. This is why every real Mars mission, every rover, every orbiter, every proposed crewed architecture is tied to a specific calendar of departures that are not negotiable. If a crewed Mars mission departs Earth today, and something serious goes wrong 6 months into the flight, there is no return ticket sitting in a drawer. The crew cannot simply turn around and come home. The orbital mechanics do not allow it. The trajectory that got them to Mars is not the trajectory that gets them back. And a rescue ship launched from Earth, even at the next available window, might take many months to arrive, by which time the emergency is over. Not resolved, just over. Compare this to Apollo 13. The reason 13 came home was that the moon is close enough to loop around and use as a gravitational sling, back onto a trajectory that intersects Earth in a few days. Mars offers no equivalent option. The planet cannot be used as a slingshot to return you to Earth on any humane timescale. Once a crew is committed to the outbound leg, they are committed. There is no aborted return that gets them home in a week. This is the first thing that Mars removes: rapid rescue. There is no such thing on a Mars mission. There is only surface stay time, careful timing, and the eventual, hopeful return along another energy-efficient trajectory when the planets align again. Now add the third layer: medicine. Astronauts, for all their training and screening, are still human beings. Human beings develop appendicitis. They break bones. They form kidney stones. They have heart attacks and strokes. They get infections. They have psychological crises. On Earth, most of these events are treatable. On the International Space Station, they can be managed at some level, and if truly serious, the crew member can be returned to a hospital within hours. On the moon, they could be returned within days. On Mars, they cannot be returned at all. Whatever happens to a crew member on Mars has to be handled with the medical equipment on board and the medical training of the crew themselves. That is it. There is no evacuation flight. There is no specialist consultation in any meaningful sense. There is only whatever the crew has already brought with them, and whatever knowledge they carry in their own heads. The list of things that could go medically wrong on a multi-year Mars mission is not short. Radiation exposure raises the long-term risk of certain cancers, though this is a slow effect rather than an acute one. Microgravity, or the low gravity of the Martian surface, causes ongoing changes in the cardiovascular system, in bone density, in muscle mass, and in the shape of the eye itself, confined environments raise the risk of infection, of psychological strain, of interpersonal conflict. The base rate of surprise emergencies, the appendicitis, the kidney stone, the sudden severe headache, does not go away just because the patient is on another planet. It might even, given the stress and the environment, go up. And every one of those emergencies on Mars is something the crew must solve alone, on a delay, with the resources they have, or not solve at all. This is why Mars, and not some point out near Pluto, is the first real threshold in this story. It is where the survival horizon first bites. Not because the ship cannot get there, not because a healthy crew cannot land, live, and eventually return under normal conditions, but because the entire chain of assumptions that has always protected human beings in space, rapid rescue, real-time conversation with the ground, resupply and demand, evacuation for serious illness, is now, for the first time, gone. An astronaut on Mars is farther from a hospital than any human being has ever been. Not just in kilometers, but in every practical sense of that phrase. And here is what makes this so easy to underestimate. Distance itself, even at Mars, is still not the thing that kills you. The vacuum of the space between Earth and Mars is no more hostile than the vacuum right next to the space station. The particles hitting your ship at Mars are only slightly different from the particles hitting it in low Earth orbit. The physical environment has not changed dramatically. What has changed is time. The time to call for help, the time to receive help, the time to endure whatever has gone wrong until it either resolves itself or does not. Distance created that time. Time is what makes Mars deadly in a way that the space station is not. You can already see the shape of the horizon starting to form. At the space station, it does not really apply. At the moon, it hovers in the background but is still generous. At Mars, for the first time, it is real. It is a hard, felt limit that mission designers have to plan around, not by moving faster than physics allows, but by carrying more, training more, redundifying more, and accepting that some categories of emergency simply will not have a solution. And Mars is the first destination. It is not the far edge of the story. It is the beginning. Because the moment you accept that a crewed Mars mission has already removed rapid rescue, real-time communication, resupply on demand, and medical evacuation from the equation, a new question opens up. What happens when a mission is not measured in months, but in years? What happens when the destination is not one planet away, but 4 or 5 or 6? What happens when the ship has to keep working and the crew has to keep functioning? Not for the length of a very long expedition, but for the length of a large chunk of a human career. Because that is what the outer solar system asks of a crew. Not months, years, sometimes many years, sometimes more. And out there, past Mars, past the asteroid belt, past the point where the sun is no longer a warm, familiar disk, but a bright star among stars, everything we have talked about so far, the rescue, the communication, the medicine, gets worse. But something new joins it. Something that does not really matter over the timescale of a Mars mission, but that begins to bite very hard the moment a journey has to be measured in years. Aging. Not just of the crew, of everything. Of the metal. Of the seals. Of the pumps. Of the filters. Of the food. Of the medicine in the cabinet. Of the software running on hardware that cannot be replaced. Of the bones inside the astronauts' bodies. of the muscles in their hearts, of the tissues behind their eyes. Out past Mars, the survival horizon stops being about a single missed rescue. It starts being about slow accumulation, about wear, about the fact that a spacecraft, no matter how beautifully engineered, is not an eternal object, and neither is a human being. And that is where we have to go next. Push the spacecraft farther, past Mars, past the asteroid belt, out into the region of the solar system where the sun is no longer a comforting disk in the sky, but a very bright point of light among other points of light. At Jupiter, the sun is about 1/27th as bright as it appears on Earth. At Saturn, 1/90th. At Uranus, 1/365th. At Neptune, close to 1/900th. A human being standing on a hypothetical platform in orbit around Neptune would look back toward the inner solar system and see the star that made them not as a source of warmth or of day and night, but as a small, hard, cold pinprick of light. The distances have grown so large that the very thing which defined life on Earth has become almost invisible, and it is out here, in this long dim corridor of the outer solar system, that the story of the human survival horizon shifts into a completely new mode. Because on the way to Mars, the killer was a single missed rescue, a specific emergency, a cardiac event with no evacuation, an infection with no specialist to consult. The horizon at Mars was defined by the loss of rapid response, and by the fact that when help is more than 20 minutes away by radio, it is not really help in any felt sense. Out past Jupiter, the story is different. The single events do not disappear, they get worse, if anything. But they are no longer the main character. The main character becomes accumulation. And the horizon in this region is no longer about whether one bad day can be survived. It is about whether an enormous number of ordinary days, stacked on top of each other, can be survived together. Let us start with the number that governs everything else out here: travel time. Even with the best chemical rockets we currently know how to build, a crewed spacecraft on a reasonable trajectory would take something like 2 to 3 years to reach Jupiter. Saturn is roughly 6 to 7 years. Uranus, more than a decade under most realistic mission architectures. Neptune, closer to 2 decades. And these are one-way numbers. A round trip, with time on station at the destination, doubles them or worse. These numbers matter because they are not months. They are meaningful fractions of a working human life. A 10-year mission takes a person from 35 to 45. A 20-year mission takes them from 35 to 55. And that is only if everything goes according to plan. Now, let us layer in the first of the accumulating killers: radiation. On Earth, human beings live at the bottom of 2 nested layers of protection. The atmosphere absorbs a huge fraction of the charged particles that would otherwise reach the surface, and above the atmosphere, the planet's magnetic field deflects most of the rest. Together, those 2 layers reduce the natural radiation environment by an enormous factor. A person walking around at sea level receives, on average, only a few millisieverts of ionizing radiation per year from all natural sources combined. On the International Space Station, that number rises. Not by an alarming factor, but by a real one. Astronauts on board typically absorb something like half a millisievert per day, which over a 6-month stay adds up to a dose that is meaningful but manageable, roughly comparable to a chest CT scan, repeated many times over. Still, the station is inside Earth's magnetic field. It is protected. Charged particles are being turned aside before they reach the walls of the modules. Once a crewed spacecraft leaves the magnetosphere, that shield is gone. From there outward, the crew is exposed to two very different categories of radiation. The first is called galactic cosmic rays. These are extremely high energy particles that arrive from all directions, produced by ancient supernova explosions and other violent events elsewhere in the galaxy. They are relatively rare, but each individual particle is fantastically energetic. Energetic enough to punch through the walls of a spacecraft, through the walls of a human body, and through the DNA inside the cells of that body, breaking bonds as it goes. Shielding helps, but only up to a point. Enough shielding to stop them would weigh so much that no rocket could lift it. The second category is solar energetic particles. These come from the sun during specific events, flares and coronal mass ejections, when the sun essentially spits out a large blob of high energy plasma into space. Most of the time, the level is low, then, without much warning, a burst arrives, and for hours or days the radiation environment near the spacecraft is thousands of times worse than baseline. On Earth, these events cause auroras and occasionally satellite malfunctions. In deep space, an unshielded crew caught in a strong solar particle event could receive an acutely dangerous dose in a single day. NASA's own estimates for a round-trip crewed mission to Mars suggest the crew would accumulate on the order of 600 millisieverts over the course of the journey, mostly from galactic cosmic rays. That is a dose more than 100 times what a person on Earth receives from natural sources over the same period. It is enough to meaningfully raise long-term cancer risk. It is not enough by itself to kill anyone quickly. But now imagine multiplying that mission duration. A crewed voyage to Jupiter and back is not a 2-year trip. It is perhaps a 5 to 7 year trip. A voyage to Saturn is longer still, and the radiation dose scales roughly with time. Double the trip, roughly double the exposure. Triple it, roughly triple. There is no magic threshold beyond which a radiation suddenly kills every crew member on the same day. What there is instead is a slow, steady increase in cumulative biological damage that at some point crosses from acceptable risk into a regime where a very large fraction of the crew is expected to develop serious radiation-induced illness during or shortly after the mission. This is what accumulation looks like. A dose counter ticking upward day after day, month after month, until the total is simply too large to have survived intact. There is one detail about galactic cosmic rays that deserves to be sat with, because it changes the shape of the problem in a way ordinary radiation discussions miss. These particles are not just fast, they are structurally different from the radiation human beings encounter on Earth. Most terrestrial radiation is either X-rays or gamma rays or beta particles, energies and particle types that biology has, in some rough sense, evolved defenses against, because low levels of them have always been present in the natural environment. Galactic cosmic rays include heavy nuclei, iron, silicon, oxygen atoms stripped of their electrons and accelerated to nearly the speed of light. When one of these ions passes through a human body, it does not deposit its energy in a small, localized region, the way an X-ray does. It leaves a track, a single ionizing streak that punches through dozens or hundreds of cells in sequence, damaging each one along the way. Biologists studying this effect have a phrase for what they see under the microscope. They call it a track structure. Imagine a single bullet passing through a stack of paper. The hole in the top page is small. So is the hole in the bottom page. But the whole stack is now perforated in a straight line, and every sheet in between has a wound. A galactic cosmic ray hitting a crew member does something like that to a column of cells, and no shield thin enough to launch is capable of stopping the heavier ones. They pass through the spacecraft and through the body and out the other side, leaving damage behind. We do not know, honestly, what a decade of this exposure does to a nervous system. Rodent studies have suggested measurable cognitive changes after doses far smaller than a long deep space mission would deliver. But rodents are not people, and their exposure profiles do not perfectly match. What we can say is that the human brain has never been tested in this environment for years at a time, and the biology gives no reason to expect that it would be untouched. Now layer in the second accumulating killer, gravity, or rather the lack of it. Every long-duration astronaut on the International Space Station has taught us something uncomfortable about the human body. It is not built for weightlessness. It was built over hundreds of millions of years of evolution to work against a very specific pull toward the ground. Remove that pull, and the body immediately starts to unbuild itself. Bones lose density at a rate of roughly 1 to 2% per month in some weight-bearing regions of the skeleton. That is faster than the bone loss experienced by an elderly person with severe osteoporosis on Earth. Muscles, especially those in the back and legs that fight gravity every day on the surface, atrophy quickly, if not constantly exercised. Blood shifts upward toward the head, changing the shape of the face and, more seriously, changing the pressures inside the skull and behind the eyes. This last effect has a name in the medical literature. It is called spaceflight-associated neuroocular syndrome, and it involves flattening of the back of the eyeball, swelling of the optic nerve, and lasting changes in vision that in some astronauts do not fully reverse after return to Earth. There is another effect that has only recently begun to be characterized clearly, and it may end up being one of the more sobering ones. The immune system, it turns out, does not function normally in space. Long-duration astronauts show reactivation of latent viruses that on Earth would remain dormant. Herpes viruses, in particular, have been observed shedding in the saliva and urine of space station crew members at rates far above what is normal on the ground. Cortisol levels are elevated. Inflammatory markers drift. T-cell function changes in ways that researchers are still working to map. None of this is dramatic on the timescale of a 6-month rotation. Crew members do not typically become seriously ill in orbit, but the underlying biology is quietly telling us something important. The immune system evolved in an environment shaped by gravity, by microbial exposure, by day and night cycles, by the subtle signals of a home planet. Remove those signals and the system drifts. What that drift looks like after 5 years, or 10, in a crew whose original vaccinations were administered decades earlier, whose gut flora has been reduced to whatever survives on packaged food, whose exposure to new pathogens is essentially zero. Nobody knows. There is no data. The extrapolation is not reassuring, but it is also not certain. On the space station, these effects are managed by a demanding daily exercise regimen. Astronauts spend roughly 2 hours a day on treadmills, resistance devices, and stationary bicycles, working hard specifically to slow the disintegration of their own bodies. Even with this, most return to Earth needing weeks of rehabilitation before they can walk normally again. Now, stretch the same conditions to years. 5 years, 10. There is no data set for that. No human being has ever spent 5 continuous years in microgravity. The longest single stay is Valery Polyakov's 437 days aboard the Mir space station in the mid-1990s, roughly 14 months. Even the cumulative records for total time in space across multiple missions are only just now reaching a few years. We do not know what a decade of microgravity does to a human body. We can only extrapolate, and the extrapolation is not encouraging. Bones do not lose density forever, because at some point they simply have very little density left to lose. Muscles do not atrophy without limit, because at some point they are not really doing much anymore. Vision changes may deepen. Immune function may drift further away from its normal baseline. Cardiovascular structure may reshape itself around the new environment in ways that make an eventual return to a full gravity world dangerous or impossible. A crew that spends a decade in weightlessness may, at the end of it, be physically incapable of surviving a landing on a planetary surface. Not because the ship failed, because their own bodies softly, quietly, over 10,000 meals and 3 million heartbeats, forgot how to be Earth animals. There are proposals for artificial gravity, of course, long-armed rotating structures, wheels or dumbbells that use centrifugal effect to press the crew against an outer wall in a way that mimics real gravity. In principle, this works. In practice, no one has ever flown a rotating habitat with a crew inside it. The engineering is complex. The size required for comfortable rotation is large, and every additional structural element is more mass to launch and more parts to eventually break. It is a candidate solution, not a solved problem. Now consider the third accumulating killer, the ship itself. There is a temptation to think of a spacecraft as a fixed object, something that is either working or not working, and that if it is working today, it will work tomorrow. This is not how machines behave. Machines wear, seals degrade, bearings develop tiny imperfections that grow with each rotation. Solder joints crack under thermal cycling. Radiation from space damages microelectronics on a timescale of years, flipping bits, degrading components, quietly reducing the reliability of every system on board. On the International Space Station, this constant wear is managed by an equally constant flow of new parts. Cargo ships arrive from Earth several times per year. Broken components are replaced. Old modules are, over long periods of time, upgraded. The station is not one continuous machine that has been running for 2.5 decades. It is more like a slowly evolving organism, most of whose original cells have been swapped out one by one. A spacecraft on a multi-year journey to the outer solar system does not have that luxury. Whatever launches with it is what it has. Every spare part must be carried on board from the beginning, or manufactured on board with tools that must themselves be carried on board. There is no cargo run. There is no resupply. A component that fails in year 7 of a 10-year mission must either be repaired with what is present, replaced from a limited onboard stock, or done without. For simple failures, this is manageable. For complex failures, it becomes an existential problem very quickly. If a component fails whose spare was not carried, or whose spare has itself already been used, the crew is now living in a spacecraft that is degraded in a specific way, and every subsequent failure interacts with that degradation. Failures compound. A ship that could tolerate one broken pump might not survive a broken pump, plus a broken filter, plus a cracked heat exchanger. Redundancy is finite. Every time it is used, there is less of it left. Consider a concrete failure to see how this compounds. In year 6 of a hypothetical crewed mission to Saturn, imagine a small crack develops in one of the ship's heat exchangers. The system's responsible for moving waste heat from the interior of the spacecraft out into space. This is not a dramatic failure. The exchanger does not explode. It simply begins to lose efficiency, gradually, over weeks. The crew notices that internal temperatures are drifting slightly higher than nominal. They investigate. They locate the crack. They have a spare exchanger on board, one carried since launch. They replace the failing unit. Now consider what has just happened. The spare is gone. The remaining redundancy for that system is 0. If another crack develops in the replacement, or if any of the 3 other heat exchangers on board fails during the remaining 4 years of the mission, the crew must repair whatever they have with the materials on hand, or accept that the ship will slowly overheat until crew survival is impossible. And repair, in this context, means a small number of astronauts with limited machining tools attempting to fix a component that on Earth would be pulled from service and replaced by a specialist team with a warehouse full of parts behind them. This is what redundancy looks like in deep space. It is not an infinite well. It is a finite number of specific spares for a finite number of specific components, and every failure eats into that reserve. A ship that launches with 3 spares of everything is not a ship that can handle any 3 failures. It is a ship that can handle 3 failures of the exact right kinds, in the exact right systems, in the exact right sequence. Any deviation from that, any failure of a component whose spare has already been used, or whose spare was never carried, is a failure with no clean solution. Now add the 4th accumulating killer. Life support. A closed-loop life support system is one of the most extraordinary pieces of engineering humanity has ever attempted. In principle, it takes carbon dioxide exhaled by the crew and recycles it back into breathable oxygen. It takes wastewater, including sweat, urine, and moisture from the air, and cleans it back into potable water. It takes food waste and biological output and processes them in ways that at least partially close the material cycle. On the International Space Station, systems of this kind already recover a large fraction of water on board and produce some of the oxygen the crew breathes. But even the best closed-loop systems are not truly closed. They lose small amounts of material to leaks, to inefficiency, to processes that cannot be reversed at all. On the space station, this loss is compensated by cargo ships bringing up fresh water and oxygen candles and new food supplies. On a multi-year deep space mission, there is no such compensation. Every unrecycled kilogram of water is a kilogram gone. Every failed subsystem is a failure the crew must patch with what they have. And then there is food itself. Food does not last forever. Even the best packaged, most carefully preserved space rations degrade over years. Nutrients break down, vitamins lose potency, taste declines, which sounds trivial until you consider what it means for a crew eating the same food for a decade. Some vitamins, in particular vitamin C, some of the B vitamins, degrade on a timescale that matters. A crew subsisting on rations that have been on board for 8 years may be receiving food that is technically edible, but nutritionally hollow. Growing fresh food on board is possible in principle, and small-scale experiments on the space station have produced lettuces and some other crops. But scaling this up to feed a crew for a decade is a serious engineering and biological problem that has not yet been solved. Medicine, too, has a shelf life. Most pharmaceuticals are stable for a few years under good storage conditions, and then begin to lose potency. Antibiotics degrade, painkillers weaken. Sensitive biologicals may be effectively unusable after a few years. A crew 10 years into a mission is carrying a medical cabinet that is, in real terms, half of what it was at launch. There is one more category of consumable that is easy to overlook and hard to solve. Consumable tools and materials, filters, seals, lubricants, adhesives, solder, wire, cleaning supplies. Every one of these is used up over time and must be replaced from stores that were loaded before launch. A 10-year mission needs 10 years of filters, 10 years of seals, 10 years of every small component that gets consumed in the ordinary process of keeping a spacecraft alive. Multiply that across every subsystem on board, and the mass budget for consumables alone becomes enormous. And unlike food, which can in principle be grown, and water, which can in principle be recycled, most of these small components cannot be manufactured from raw materials with any tool a spacecraft can plausibly carry. They must be brought. Now put all of this together, layer by layer, on a single crew. The radiation counter is ticking. The bones are quietly losing mass. The eyes are quietly changing shape. The ship's seals are quietly leaking. The recycling system is quietly falling behind. The medicine is quietly weakening. The food is quietly emptying of vitamins. And none of these things is a single crisis. They are all just in the background, getting worse. This is the shape of the survival horizon in the outer solar system. It is not a wall. It is a slope. A gradual, patient slope down which every mission is sliding from the moment it leaves Earth. Solving one problem does not stop the slide. It only slows one component of it. The crew can exercise for hours a day, and still their bones will thin. They can shield some of their sleeping quarters, and still the radiation will accumulate. Somewhere along that slope, a crewed mission becomes, in the honest engineering sense, unlikely to succeed. Not impossible, just unlikely. And the definition of success is not merely that the crew is still breathing at the end of the mission. It is that they are still capable of doing the mission. Capable of landing, of working, of operating equipment, of making decisions, of returning home, of getting out of the capsule and standing on Earth again as functioning human beings. An arrival with a crew too injured, too irradiated, too weakened, too depleted to do anything useful is not a successful mission. It is a slow, expensive tragedy that happens to end near a planet. There is one more accumulating killer that has not been named yet, and it may be the hardest of all to engineer around: isolation. Human beings did not evolve to spend years in confined metal boxes with the same handful of other human beings, cut off from every other social contact, with no meaningful ability to leave. We know a little bit about what this does to us because we have tried it in careful, monitored ways on Earth. The Mars 500 experiment, run in Russia between 2010 and 2011, sealed 6 volunteers into a mock spacecraft for 520 days to simulate a full Mars mission. They stayed indoors the entire time. They ate stored food. They communicated with the outside world on artificial delays. And even in that simulation, where every participant knew that a door could be opened in an emergency, researchers observed measurable changes. Sleep patterns drifted. Some crew members became sedentary, spending more and more time inactive. Interpersonal frictions built up. Motivation waxed and waned. Antarctic overwintering stations, where small teams spend 6 to 9 months in near total isolation during the polar night, tell a similar story. Depression rates rise. cognitive performance slips in subtle ways. Interpersonal conflict, in some cases, becomes serious enough to affect station operations. And these are still teams on Earth with an eventual guaranteed return, with the psychological anchor of a home planet under their feet, with the knowledge that if things truly fell apart, help exists. There is a subtler version of the isolation problem that does not involve any single dramatic breakdown, and it may be the more common one. Not psychosis, not suicide, just erosion. The slow, quiet loss of motivation that comes from doing the same tasks, in the same environment, with the same people, for a length of time longer than any human being has ever tried before. Astronauts who have spent 6 months on the space station have described, in interviews after their return, a phenomenon that does not have a good clinical name, but that everyone in the field recognizes. Somewhere in the middle of a long rotation, the sharpness goes out of things. The daily routine, which was fascinating in the first month, becomes ordinary. The view of Earth from the cupola, which was overwhelming at first, becomes background. The crew is still competent. They're still doing their jobs, but something has quietly dulled, and it takes deliberate effort to keep the mission feeling meaningful. Now, stretch that from 6 months to 6 years to 10. The erosion is not a crisis. It is not a headline. It is just the slow leaching of the thing that made the crew members good candidates for the mission in the first place. Their engagement, their curiosity, their sense that what they are doing matters. When that fades, mistakes creep in. Not dramatic mistakes, small ones. A checklist item skipped because it feels routine. A concern not raised because it does not seem worth mentioning. A conversation with the ground truncated because there is nothing new to say. And in a spacecraft where every checklist item exists for a reason and every concern might be the first sign of a compounding failure, small mistakes are how missions quietly fall apart. Now imagine years, not months. Imagine no door that opens. Imagine no rescue plane that could ever be called in. Imagine that the same 6 or 8 faces are the only faces the crew will see for the entire remaining duration of the mission, which may still be many years away. Imagine that a member of that crew develops a serious mental illness, a psychotic episode, a suicidal depression, a severe personality change, with no way to remove them from the environment, and no way to bring in professional help. This is not hypothetical. It is a known risk of long-duration deep space missions, and it does not have a good solution. Careful crew selection can reduce the odds, but it cannot eliminate them. Human beings sometimes become unwell. When it happens on Earth, there are places to go. On a decade-long voyage to Neptune, there is only the ship. The isolation problem is often mentioned last in these discussions, as if it were a soft, secondary concern next to the harder physics of radiation and life support. It is not. It is a hard limit in its own right. There is a length of confinement past which, for most human beings, functioning breaks down. We do not know exactly where that length is because we have never fully tested it. But we know it exists because everything we know about human psychology says it must. And this is where the outer solar system quietly draws the practical survival horizon for a single crew, not at any one distance. At the point where the accumulated cost of everything we have talked about, radiation, bone loss, wear, life support drift, medical shelf life, isolation, exceeds what any plausible spacecraft can carry and any plausible crew can bear. Some of the numbers here are honestly uncertain. estimates for how long a well-designed crewed mission could remain healthy in deep space range from a few years to perhaps a decade or two, depending on shielding, propulsion, rotation, medical capability, and mission design. The horizon is not a coordinate, it is an envelope. Inside it, missions are hard. Outside it, missions are for a single human crew making the complete journey, not really missions anymore. They are one-way trips whose end nobody survives to see. And here is where the word survival needs to be pulled apart carefully, because it is doing more than one job in this discussion. There is survival in the sense of being alive at the end of the mission. There is survival in the sense of being functional at the end of the mission. And there is survival in the sense of being able to do the thing the mission was launched to do. These are not the same. A crew that arrives at Saturn after 8 years in space, whose bones have thinned to the point that landing on any solid surface risks fracture, whose eyesight has degraded, whose immune systems are compromised, whose cognitive sharpness has faded, is a crew that is alive in the medical sense. They are breathing, their hearts are beating, but they are not in any operational sense capable of completing an expedition. They cannot climb into a lander and explore a moon. They cannot conduct extended surface operations. They cannot repair a serious equipment failure that requires strength or dexterity or sustained concentration. They can, at best, orbit their destination and watch it through instruments, and then endure the journey home in whatever condition they can manage. A mission that ends this way has not really succeeded. It has been survived, in a technical sense, but the reason it was launched, for human beings to reach a place and do work there that machines could not do alone, has quietly evaporated somewhere in the accumulated damage of the transit. We already have vivid examples of what lies past that envelope. They are just not carrying anyone. Voyager 1, launched in 1977, has been traveling outward from Earth for nearly half a century. It is now more than 24 billion kilometers away, well past the boundary where the sun's influence gives way to interstellar space. Its instruments still function, in a diminished way. Its radio still whispers back across the dark, arriving in ground stations as a signal so faint it is measured in trillionths of a watt. Voyager 2, its sibling, is close behind on a different trajectory. They are proof that a well-built machine can survive in deep space for decades. They are also proof of exactly the point this episode is trying to make. Because no human being is on board either of them, and no human being ever could have been. Voyager has already outlived the practical survival horizon of any conceivable crewed mission that could have been launched at the same time on the same trajectory. It is not a spacecraft in the sense that Apollo was a spacecraft. It is a machine going somewhere no crew could follow. So we have found the shape of the horizon inside the solar system. Close to Earth, it does not apply. At the moon, it is generous. At Mars, it appears for the first time as a real limit on rescue and medical care. Between Mars and roughly the outer planets, it becomes an envelope defined by accumulation, of dose, of wear, of loss, of confinement. Somewhere out there, without any single obvious line, a crewed mission becomes something we can imagine designing, but not something we can honestly expect anyone to survive intact. But even this is not the end of the story. Because the solar system, as vast as it is only the beginning of the map. The sun is one star out of hundreds of billions in our galaxy. The nearest of those other stars is not measured in kilometers or in astronomical units. It is measured in a unit that says something honest about the trip, light years. And the moment we start talking about light years, everything we have discussed so far, the radiation, the bones, the wear, the isolation, the shelf life of food and medicine, collides head-on with a limit that is bigger than any of them. The length of a human life. Step outside on a clear night, in a place far enough from city lights that the sky is actually dark, and look toward the southern sky. If you are anywhere in the southern hemisphere, or in the far south of the northern hemisphere, there is a bright star there called Alpha Centauri. Most northern viewers cannot see it at all. It never rises above their horizon. It looks like one star to the naked eye. It is actually a system of 3, orbiting each other in a slow, gravitational dance. 2 of them, Alpha Centauri A and B, are roughly sun-like. The third, a small red dwarf called Proxima Centauri, is the closest star to our own. Proxima Centauri sits about 4.24 light-years away from Earth. That is the nearest of the trillions of other stars in the observable universe. The closest one, the neighbor. Now translate that distance out of the astronomer's shorthand and into something a spacecraft can actually feel. 1 light-year is the distance that light, moving at 300,000 kilometers per second, covers in 1 year. 4.24 light-years is roughly 40 trillion kilometers. Compared to that number, everything we discussed earlier, Jupiter, Saturn, Neptune, Voyager 1 drifting past the edge of the sun's influence, collapses into rounding error. Voyager 1, after nearly half a century of continuous flight, has covered less than 1/5000th of that distance. This is the moment in the story where the phrase interstellar space stops being a general mood and becomes a concrete engineering problem. Because if there is any destination in the universe that most clearly frames the human survival horizon, it is Proxima Centauri. It is the friendliest possible test case, and even the friendliest possible test case is brutal. The first thing to understand is that at the speeds we currently know how to build, this trip is not survivable at all. Not in the practical sense we have been using throughout this walk outward. Not even close. Voyager 1 is moving away from the sun at about 17 kilometers per second. That is genuinely fast by any human standard. And at 17 kilometers per second, it would take Voyager, if it were pointed the right way, roughly 75,000 years to reach the distance of Proxima Centauri. 75,000. That number does not compute against a human life. It is that 75,000 years is longer than recorded human civilization. The wheels of Voyager-style propulsion do not merely miss the survival horizon. They miss it by a factor of about 1,000. There is another way to feel that number, and it may be more useful than the raw arithmetic. If a Voyager-class probe had been launched not in 1977, but during the height of the Roman Empire, say at the coronation of the Emperor Augustus, and had been traveling continuously ever since at 17 kilometers per second, it would still not have arrived at Proxima Centauri today. It would be roughly 2.5% of the way there. The remaining 97.5% of the journey would still stretch ahead. That is what 75,000 years means in relation to a chemical rocket. It is a timescale in which entire civilizations rise and fall, while the ship covers a rounding error of its route. So the honest question is not whether current chemical or gravity-assisted spacecraft can carry a crew to another star. They cannot. The honest question is what speed a spacecraft would need to reach, and what happens to the crew, the ship, and the mission at each of those speeds. Because the story of interstellar travel is really a story about a set of thresholds, each of which trades one problem for another. Let us walk through them. The first threshold is roughly 1% of the speed of light. That is 3,000 kilometers per second, or about 180 times faster than Voyager. At 1% of light speed, a trip to Proxima Centauri takes about 424 years. One way. Sit with that for a moment. 424 years is longer than the age of most modern nations. It is longer than the entire history of powered flight, of electric light, of recorded music, of every major medical breakthrough on Earth. No individual human being who leaves at the start of that mission will be alive when it arrives. Not their children, not their grandchildren, not their great-grandchildren. Something like 15 to 20 generations will have lived and died on board before the ship crosses the finish line. This is not a mission a single crew survives. It is a mission a lineage completes. We will come back to what that implies because it is central to the whole episode. But first, let us look at what speeds would actually put the destination inside a single human lifetime. To reach Proxima Centauri in, say, 40 years, a career length, roughly the working life of an adult human being, a spacecraft would need to travel at about 10% of the speed of light, 30,000 kilometers per second, around 1,700 times faster than Voyager. This is what most serious interstellar concepts aim for, at least aspirationally, because it is the ballpark in which the phrase crewed mission stops being an oxymoron. And 10% of light speed is the point at which everything we thought we understood about spacecraft engineering breaks in new and creative ways. Start with the energy. Kinetic energy grows with square of velocity. Doubling your speed does not double your energy requirement, it quadruples it. Going from Voyager's 17 kilometers per second to 30,000 kilometers per second is not a factor of 1,700 more energy. It is roughly a factor of 3 million more energy per unit of mass carried. Every kilogram of spacecraft you accelerate to 10% of light speed carries a kinetic energy that dwarfs anything humanity currently produces on that scale. To make that scaling concrete, consider a crewed spacecraft with a total mass of 1,000 tons, modest by interstellar standards, comparable to a small submarine. To accelerate that mass to 10% of the speed of light requires depositing kinetic energy of roughly 4.5 times 10 to the 21st joules into it. That is a number that means nothing to most people, so let us translate. It is approximately the entire annual energy consumption of every human being on Earth combined. Not for a year of the mission, for a single acceleration phase at the beginning to bring the ship up to cruise speed. And then, at the far end, roughly the same amount again to slow it back down. Even if that energy could be produced, it has to be delivered to the ship, on the ship, at a controlled rate over the acceleration phase. And whatever propellant is used to convert that energy into thrust becomes part of the ship's mass, which itself has to be accelerated, which requires more propellant, which is itself mass that has to be accelerated. This spiral is the rocket equation, and it is unforgiving. It is the reason why every serious interstellar concept either abandons onboard propellant entirely, as the laser sail does, or invokes forms of energy generation that we do not yet know how to build. This is why the propulsion problem for interstellar travel is not really a rocket problem in the ordinary sense. Chemical rockets cannot do it, not even in principle, because the fuel required to reach that speed would weigh more than the entire observable universe if you tried to do it with chemistry alone. Nuclear pulse concepts, in which a spacecraft is pushed by a series of controlled nuclear explosions behind it, could, in principle, reach a few percent of light speed. Studies from the 1960s, most famously the Orion concept, produced serious engineering sketches showing this was not obviously impossible, but it involved detonating thousands of nuclear devices to move a single ship, and no such vehicle has ever been built or ever will be under current treaties. Fusion drives, in which a spacecraft uses controlled fusion of light nuclei to generate thrust, are the more polite version of this idea. In principle, a fusion-driven ship could reach roughly 10% of light speed. In practice, we do not yet have working fusion power on Earth in an ordinary generator, let alone in a package small enough and light enough to sit inside a spacecraft. It is a plausible future technology. It is not a present one. The most exotic serious concept is the laser-pushed light sail. A very thin, very reflective sail is deployed behind or in front of the spacecraft, and a powerful laser array back home on Earth or in orbit shines onto it, transferring momentum through photon pressure. Because the fuel is not carried on board, it stays on Earth as the laser array. The ship itself can be extremely light. The current best known example of this concept is the breakthrough Starshot proposal, which imagines using a large ground-based laser to accelerate a fleet of very small, gram-scale probes to about 20% of the speed of light, aimed at the Alpha Centauri system. Notice something about breakthrough Starshot. The probes are grams, not tons, not thousands of tons, as a real crewed spacecraft would need to be. Grams. They carry no life support, no shielding, no medical bay, no crew, no room for a crew. They are intended as instrumented postcards, tiny cameras and radios that will fly past Proxima Centauri decades from now and, if all goes well, send back a small trickle of data before disappearing into the dark forever. The Starshot design is honest about what it is. It is an interstellar probe concept, not an interstellar crewed mission concept. The engineers who designed it are not claiming that a human being can ride one of those sails. Nobody could. A human body attached to a sail being pushed at 100,000 gravities of acceleration is not, at the end of the acceleration phase, a human body anymore. Which brings us to the second consequence of high speed. Acceleration itself is a problem. If you want to reach 10% of light speed and have your crew survive the boost phase, you cannot accelerate at whatever rate is technologically convenient. You have to accelerate at a rate a human body can tolerate. Sustained accelerations above roughly 1 gravity are already stressful over long periods. Above 2 or 3 gravities, they become debilitating within days. So a crewed ship needs a long, gentle boost, perhaps months or years of continuous thrust at about 1 gravity, to reach cruise speed. That in turn means the propulsion system must run continuously for that entire time, without failure, without maintenance, without pause. Now add the third consequence: deceleration. This is the part that most fictional stories quietly skip. Reaching another star at 10% of light speed is only useful if you can also stop when you get there. Otherwise, you fly past the destination in a matter of hours and disappear back into interstellar space forever, having taken 42 years to arrive and roughly a single afternoon to leave. To actually orbit Proxima Centauri, or to land on a planet around it, The ship has to decelerate from 10% of light speed down to essentially zero relative to the destination system. And deceleration takes essentially the same energy as acceleration. You have to do the entire boost problem again in reverse on the far end of the trip. For a nuclear or fusion-driven ship, this doubles the fuel requirement. For a laser sail, this is even worse. The laser array is back on Earth. It cannot push the sail from behind at the destination. Various clever schemes have been proposed. Magnetic sails that break against the interstellar medium, small onboard rockets, using the destination star's own light. But none of them are proven, and all of them add mass and complexity to a ship that has to survive decades in transit before it needs any of it. Now add the fourth consequence: dust. Interstellar space is not truly empty. It contains, sparsely but persistently, tiny grains of dust and stray hydrogen atoms. At normal orbital speeds, these are irrelevant. A microscopic grain of silicate drifting through a spacecraft's path deposits essentially no energy. At 10% of the speed of light, the same grain becomes a bullet. The kinetic energy of a tiny mass grows with the square of velocity, remember? And at these speeds, even a single grain of dust delivers energy comparable to a small chemical explosion when it hits the front of the ship. This is not a hypothetical. It is a straightforward consequence of the physics. A spacecraft moving at 10% of light speed through the interstellar medium is being sandblasted continuously by particles that individually would be invisible on Earth, but that at these speeds each deliver a bright flash of energy to the front of the vehicle. Over a 40-year cruise, the accumulated damage to the leading surfaces would be enormous. The ship needs a forward shield, and the forward shield has to be thick enough to survive not just average dust, but the occasional larger particle. And every kilogram of shield mass is a kilogram that must itself be accelerated at the start and decelerated at the end, doubling the propulsion problem for its own sake. The engineering solutions that have been sketched for this: a large ablative shield of ice or metal ahead of the crew module, a magnetic field to deflect charged particles, a thin dust vaporizing beam that clears the path. All work in principle. None have ever been built at scale, and every one of them adds mass, complexity, and additional failure modes to a spacecraft that has to remain functional for decades in an environment where nothing can be repaired. There is a related problem that gets discussed less often than dust, and it is worth naming: heat. A spacecraft moving through the interstellar medium at 10% of the speed of light is not just being struck by dust. It is being struck by stray hydrogen atoms, one after another, in a continuous stream. Each individual collision deposits a small amount of energy into the ship's forward surface as heat. The rate of these collisions is small in absolute terms, but it is continuous, and over years of cruise it adds up to a heating load that the ship must actively radiate away or eventually cook itself from the inside out. Radiating heat in space is not the simple problem it seems. Vacuum is an excellent insulator. The only way for a spacecraft to shed excess heat is through infrared emission from its outer surface, which requires large radiator panels facing empty space. Those panels are themselves mass. They are themselves things that can fail, and on a crewed mission, they must operate continuously, without maintenance, for the full duration of the transit. If they fail, the interior temperature rises, the crew's environment becomes untenable, and there is nothing the crew can do about it that does not involve going outside a spacecraft, moving at 30,000 kilometers per second. Now, let us finally, honestly, layer in the accumulating problems we walked through earlier. The radiation, the aging, the isolation. Because they do not go away when you speed the ship up. They come along for the ride and they play out against a longer clock than any human lifetime. Radiation. In deep interstellar space, the crew is exposed to essentially the raw galactic cosmic ray background, with no help from the sun's magnetic field. Over a 40-year cruise, cumulative dose without heavy shielding would be catastrophic. Shielding adds mass. Mass slows the ship. It is the same trade-off as with dust, only worse. Aging of the ship. On a Mars mission, we worried about seals failing after a few years. On a Neptune mission, after a decade or two. On a Proxima mission at 10% of light speed, the ship has to keep working for something like 42 years each way. That is longer than the operational lifetime of most technology ever built. Voyager, our best real-world example of long-duration machine endurance, has only recently passed that age itself, and it is a small, simple robotic probe with no crew and no life support. A crewed interstellar ship would be orders of magnitude more complex, with correspondingly more things that could fail. Aging of the crew. Here we arrive at the wall. Assume for a moment that every engineering problem we have just described is somehow solved. Assume the propulsion works. Assume the shielding works. Assume the life support recycles perfectly. Assume the medicine remains potent for 4 decades. Assume the crew never has a single serious interpersonal breakdown, never loses their minds, never turns on each other. Assume all of it. A crew member who leaves Earth at age 35 on a 42-year one-way trip arrives at Proxima Centauri at age 77. If they turn around immediately and come back, assume generously that this is even possible. They arrive at Earth at age 119. And this is assuming, generously, that the crew member is capable of anything meaningful on arrival. A person at 77 who has spent 42 years in a spacecraft, even a spacecraft with a rotating gravity, with the best possible shielding, with a full medical bay, is not the same person who left Earth at 35. They have lived through radiation doses no human has lived through before. They have endured an isolation none of us has data for. Their body has aged 4 decades in a controlled but unfamiliar environment. Whatever exploration is meant to happen at Proxima Centauri has to be done by that person, at that age, in that condition, without support, without rescue, without any option to say the mission is too much and go home. There are no 119-year-old human beings. There have been, in the entire recorded history of our species, a very small number of people who lived past 115, and none of them were doing meaningful work in the last decades of their lives. The oldest reliably documented person in modern history, Jeanne Calment, lived to 122. She did not perform spaceflight tasks in her final years. So, a round trip to the nearest star at 10% of the speed of light is, for a single crew, essentially a one-way trip. The people who leave Earth are not the people who come home, because the people who leave Earth do not come home at all. They arrive somewhere else, alien and old, and if there is anything for them to do at the far end, they have perhaps a decade to do it before their bodies give out. And this is Proxima Centauri, the closest possible destination. Now consider what happens if the star of interest is not 4 light years away, but, say, 12, or 40, or 400. There are perhaps a few dozen stars within about 15 light years of the Sun. Beyond that, distances scale rapidly, and even at 10% of light speed, no crew of human beings can reach most of them within one lifetime. The Milky Way galaxy is about 100,000 light years across. At 1/10 of light speed, crossing the galaxy takes 1,000,000 years. The nearest large spiral galaxy, Andromeda, is about 2.5 million light years away, which at that speed is 25 million years of transit. This is where the phrase we started with becomes literal. There is a distance no one can survive. Not because space kills at that distance, because the distance corresponds to a journey that no living human being can endure long enough to see the other end. You can push the speed higher, of course, and every increment helps. Half of light speed cuts the Proxima trip from 42 years to about 8.5. 90% of light speed cuts it further, and time dilation begins to enter the story in a way that helps the traveler, but not the family they left behind. At relativistic speeds close to that of light itself, the crew on board a hypothetical starship would experience less time than the outside universe. A voyage that Earth measures as decades could feel to a crew moving fast enough like a much shorter passage. This is real physics, tested in particle accelerators and in atmospheric muons, and it is not in dispute. There is something worth pausing on in the time dilation scenario, because it is often presented as a solution to the interstellar problem, and it is not really one. Consider a hypothetical starship that reaches 99% of the speed of light and travels to a star 40 light years away. On board, the crew experiences perhaps 6 years of transit. On Earth, more than 40 years pass. When the crew arrives, they are still young. That part is true. But now think about who they arrive as. Their families on Earth have aged 40 years. Their parents are likely dead. Their siblings are approaching old age. Their children, if they had any, are older than they are. The world they knew has been replaced by a world they never lived in. Every institution they trusted, every language they used, every social norm they took for granted, has drifted forward by 4 decades without them. And if they turn around and return, another 40 years pass on Earth, while they experience another 6 on board. By the time they come back, they left behind 80 Earth years. They have been in space for 12 subjective ones. Everyone they ever knew is dead. Time dilation does not preserve the traveler in any meaningful cultural sense. It preserves their biology. It does not preserve their world. And the question of whether that is a form of survival or a form of very slow, one-way exile is not one that physics can answer. It is a question that a species has to answer for itself before it decides whether to send anyone. But nothing in this story is free. Each increment of speed toward light speed makes the engineering problems we described earlier worse, not better. More energy required per kilogram, more extreme deceleration, more kinetic energy in every stray dust grain, denser shielding required, sharper radiation background. Every one of those problems trades a lifespan constraint for an engineering constraint, and neither goes away entirely. The lifespan wall is real, and it is not lifted by simply going faster. It is only relocated. What faster travel does is trade one form of the wall, died of old age before arrival, for another form of it, arrived at a destination whose sending civilization no longer exists. So we are left with a set of choices that a species like ours has to face honestly. The first choice is to accept that interstellar travel is not, in any reasonable timescale, a thing a single crew of human beings will complete round trip. The people who leave Earth do not come back. The mission, if it is done at all, is a one-way commitment. The second choice is to accept that even the one-way trip for most destinations is longer than a single human life. That means the ship must either carry more than one generation of crew, or the crew must find some way to endure a passage that outlasts them. Two speculative responses appear at this point in the story, and both deserve to be named clearly, because they are the responses most often invoked when this problem is discussed. The first is suspended animation. The idea is that a crew is placed into some form of very slow biological state. Deep cooling, metabolic slowdown, some medical process that reduces the rate at which the body ages and consumes resources for the bulk of the voyage. They are woken up at the destination or periodically during the trip for maintenance. Suspended animation, as of today, is not a technology that exists for human beings. There is real research into related areas. Certain surgical procedures use controlled cooling to slow metabolism for hours during operations. Studies of hibernating animals, from ground squirrels to certain bears, hint at biological mechanisms that reduce metabolic rate dramatically. But no human being has ever been placed into a true suspended state for a period longer than emergency medical procedures allow, and revived without damage months or years later. The technology is a candidate. It is not a demonstrated capability. Treating it as if it were solves the human survival horizon problem on paper and nowhere else. The second speculative response is the generation ship. Here the idea is different. The crew that leaves Earth is not the crew that arrives. The ship carries an entire small community, perhaps a few hundred people, perhaps a few thousand. During the voyage, they live, marry, raise children, die, are buried, and are replaced by the next generation. The children learn from their parents, the grandchildren learn from their grandparents' recorded lessons. When the ship finally arrives at its destination centuries later, the people stepping off are the great-grandchildren of the ones who set out. Consider what a generation ship actually requires, beyond the propulsion and the shielding and the life support. It requires a small society capable of governing itself across centuries with no external oversight. It requires a system of education that can be sustained across generations of teachers who never leave the ship, teaching curricula that were designed by people who died long before the current teachers were born. It requires an economy of labor. Someone has to grow the food, maintain the systems, make the medical decisions, resolve the disputes. That functions across time frames in which every specific human involved is replaced multiple times. It requires answers to questions no closed society has ever had to answer before. What happens if the third generation on board decides they do not want to complete the mission? What happens if a subgroup, 3 centuries in, comes to believe that turning back is preferable to arriving? What happens if the ship's population grows beyond what its life support can handle, and difficult decisions have to be made about who eats and who does not? What happens if a serious ideological disagreement develops between factions that cannot be separated because there is nowhere to go? None of these questions is science fiction. They are the ordinary questions of any human society scaled up to a duration and a confinement that no ordinary society has ever faced. And the answers matter because a generation ship whose passengers rebel, or fracture, or lose the will to continue does not arrive at its destination in a useful condition. It arrives as whatever the failure produced, if it arrives at all. This is a coherent idea. It is also a very different thing from the notion we started this story with, because a generation ship is not one human crew surviving the journey. It is a small society passing through space, whose founding members die on board, whose middle members are born and die on board, and whose final members arrive at a world their ancestors chose, but they themselves never had the option to reject. The people who leave Earth do not arrive at Proxima Centauri. Their descendants do. And those descendants are, in a real and biological sense, a different population from the one that departed. They may know Earth only from stories. They may have never breathed air outside the ship. They may be, by the end, a species subtly changed by centuries of life in a metal cylinder, under artificial gravity, eating recycled food, exposed to a slightly different radiation background than any Earth animal. This is why the phrase we start with has to be handled with care. There is not a fixed distance in kilometers past which every human being drops dead. There is instead a moment along the outward journey where the meaning of the mission changes, where the assumption that the same people who leave will be the same people who arrive breaks apart, where survival stops being a question of individual endurance and becomes a question of what a mission even is. Machines do not have this problem. Voyager does not care that it has been flying for 50 years. It does not miss the Earth it left. It does not develop kidney stones. It does not sleep. It does not require food that has to remain nutritious for 4 decades. If a robotic probe is well made and well aimed, it can quietly cross distances that no human crew could ever survive, and it can send back data from those distances, and it will do so without complaint until its power finally fails. This is the honest, quiet asymmetry of interstellar travel. Machines can go there. People, in the ordinary meaning of the word, cannot. Not because space is more violent at 4 light years than it is at 400 kilometers. It is not. The vacuum is the same. The physics is the same. The stars are the same stars, only slightly closer. It is because the crossing takes time, and time is what a human body cannot spend without limit. So we now have the shape of the survival horizon at interstellar distances. Under any realistic mission architecture using propulsion we understand, a single crew of human beings cannot survive a round trip to another star. Under aggressive but plausible propulsion, a one-way trip to the nearest star is barely inside a single crew's lifespan, and only if everything else works perfectly, which is not how anything ever works. Under anything slower, the mission becomes a generation ship, a very different kind of thing, or a robotic mission with no crew at all. And this leaves us with the question that this whole walk has been building toward. If distance in space, past a certain point, becomes a journey no original traveler can survive, then what does it mean to say that humanity has reached that place? What does exploration look like when the reacher and the traveler are no longer the same person? What is the difference between a species that can send its machines and its descendants across the sky, and a species that can send its own individuals there and bring them home again? Because those are 2 different definitions of exploration, and the boundary between them may not be a wall in space at all. It may be a boundary in what we are willing to call ourselves, once we accept that the universe is bigger than any single life we can live inside it. That is where we have to go next. We have arrived at the honest ending of the story, and it does not sit where most people expect it to sit. If you had asked me, before we started this journey, where the distance no one can survive actually lay, I would have guessed at some coordinate. Some number of kilometers past which the vacuum becomes too much, or the radiation becomes too much, or the isolation becomes too much. A line drawn on a star chart with a warning label attached. But we've walked out from Earth together now, one step at a time, and the line has refused to appear. At low Earth orbit, the horizon barely applied. At the Moon, it was still generous. At Mars, it appeared for the first time as a real limit, drawn not by physics but by the loss of rescue and the birth of communication delay. In the outer solar system, it deepened into an envelope of accumulation. Radiation dose, bone loss, machine wear, medicine going stale, food going hollow, sanity being tested by years of confinement. And in interstellar space, the envelope collided with the length of a human life itself, and there was nothing left to negotiate with. What we have found is not a wall. What we have found is a mismatch between the size of the universe and the length of the time a human being gets to spend inside it. The universe is enormous, a human life is short, and the tools we have for crossing the enormous thing operate on timescales that do not fit inside the short thing. That is the survival horizon. That is the distance no one can survive, not because space kills, but because time runs out. And so, before we close, I want to be honest with you about what humanity's speculative responses to this actually are, in the sober sense. Not what science fiction promises, what the peer-reviewed literature and the honest engineering studies suggest. Because these are the ideas that get invoked whenever someone waves at Proxima Centauri and says, "We will get there eventually." And they deserve to be looked at plainly in the order of their maturity. The first and least speculative is artificial gravity. This one is closer to solved engineering than to fantasy. If you take a large enough structure and rotate it at the right rate, the outward centrifugal effect creates a force against the outer wall that feels, to the people standing there, indistinguishable from real gravity. Rotate a large enough ring at the right speed, and a person on the inside of it walks around normally. Their bones and muscles under a familiar load, their blood pooling in their feet, the way it has done for 4 billion years of Earth evolution. This does not require new physics. It requires size. The larger the rotating structure, the slower it can spin while still producing one gravity, and the more comfortable it is for the people inside. Small rotating structures make people feel sick, because the difference in centrifugal force between their head and their feet is too large. Very large ones. Hundreds of meters across at minimum, kilometers across for real comfort. Solve that problem, but at the cost of enormous mass, enormous engineering complexity, and enormous cost. Nobody has ever flown a rotating habitat with a crew inside it. Not once. Every human being who has spent months or years in space has done so in the free-floating microgravity of orbital modules, with the results for their bodies that we walked through earlier. The bone loss, the vision changes, the immune drift. Artificial gravity is a candidate solution to the bone and muscle problem. It is not, at the moment, an implemented one. The next tier up in speculation is suspended animation. We touched on this earlier. The idea is that a crew could be placed into some form of very deep biological standby for the bulk of a long voyage, waking up at the destination or at intervals for maintenance. If the metabolic rate could be slowed sufficiently, the biological clock could effectively be paused. A trip of a century could become, subjectively, a few years of experience. We do not have this technology for human beings. We have adjacent knowledge. Certain surgical procedures use controlled cooling to slow a patient's metabolism for hours at a time. Studies of hibernating mammals, ground squirrels, some species of bear have shown remarkable metabolic changes that no human being naturally experiences. There is real research going on in this area, some of it directly motivated by space agencies interested in easing long-duration missions. But there is no demonstrated method by which a human being can be placed into a genuinely slowed biological state for years, and then revived without significant damage. This may become possible in the coming century. It may not. Treating it as if it is already available or clearly around the corner would be dishonest. It is a candidate. It is not a solution. The next tier is radical life extension. If a human life could be reliably extended from about 80 years to, say, 300, then the arithmetic of interstellar travel changes dramatically. A one-way voyage to Proxima Centauri at 1% of the speed of light, 4 centuries, is unreachable for an 80-year lifespan. It is reachable, at least in principle, for a 300-year one. Longer lifespans push the survival horizon outward more effectively than any propulsion improvement, because they change the denominator of the equation rather than the numerator. But radical life extension is not a solved problem either. The current best estimates for human lifespan under optimal conditions cluster around 120 years, and even reaching that upper bound remains extraordinarily rare. Research into aging biology has produced interesting results in laboratory animals, some of which live meaningfully longer under specific interventions. Whether any of that translates to human beings, and whether we can safely add decades or centuries to a normal life, is not something anyone knows. The next tier up gets stranger: embryo missions. The idea here is to send not a crew, and not even a set of frozen adult humans, but a stored population of embryos or genetic material, along with an automated system capable of gestating and raising them at the destination. The ship arrives at another star with no living human on board at any point during the transit. It then, using stored biological material and machinery, creates a first generation of humans at the far end who are raised by artificial systems and eventually inherit the destination world. This is a thought experiment more than it is a proposal. It involves enormous unsolved problems in artificial gestation, in early child rearing without human caregivers, in the psychological development of children raised by machines, in the ethics of committing unborn people to a fate they cannot consent to. It appears in the academic literature not because anyone thinks it will be attempted soon, but because it illustrates just how far the concept of a crewed mission has to be bent before it can honestly fit across interstellar distances. Each of these ideas, artificial gravity, suspended animation, radical life extension, embryo missions, self-repairing habitats, closed-loop biospheres, solves a specific piece of the problem. None of them solves the whole, and none of them, at the level of demonstrated engineering, allows an ordinary human crew to leave Earth today and stand alive on the surface of a planet around another star. And this brings us finally to the distinction that this whole story has been building toward. There are two very different things that can happen at the far end of a very long journey. The first is arrival. The second is survival. Arrival is when a spacecraft reaches a destination. It is a physical event. A machine crosses a distance and is now in a new place. Whether or not anyone alive is on board is not, from the point of view of orbital mechanics, relevant. The ship gets there or it does not. Survival is what happens to a human being during the crossing. It is a biological event. A person leaves one place and at some later time is alive and functional in another. Whether the ship carrying them also arrives is only half of the question. The other half is whether they, personally, are still there to see it. These two events used to travel together. For every human journey in history, up to and including the Apollo missions, the ship and the crew arrived at essentially the same time, in essentially the same condition. The story of a voyage was the story of a group of people going somewhere and being there when they got there. That is what exploration has always meant. Somewhere out past the outer solar system, and certainly by the time we start talking about other stars, the two events separate. The ship can arrive without the crew surviving. The crew can, in some sense, survive by being replaced generation after generation, without any individual person actually arriving. And in the extreme case, the case that best answers the question we start with, a machine can reach a destination that no living human being who ever left Earth was capable of reaching in one lifetime. That last case is already happening. Right now. In the real universe. And it has been for decades. Voyager 1 left Cape Canaveral in 1977. It is now, at the time of this recording, roughly 48 years into its journey. It has flown past Jupiter, Saturn, and the outer boundaries of the Sun's influence, and it is now in the region we call interstellar space, where the solar wind no longer dominates and the wider galactic medium takes over. It is more than 24 billion kilometers from home. It is the most distant human-made object that has ever existed. There is no one on board. There never was. And yet, in a real sense, humanity has reached that place. A machine we designed and built and aimed is out there, in a region no crude spacecraft has ever come close to, sending back a signal so faint that receiving it on Earth requires some of the most sensitive radio telescopes ever constructed. Every night, if we listen carefully, we can still hear it. That signal has been traveling for over 22 hours by the time it arrives. Voyager is not going to another star soon, in any meaningful sense. If nothing deflects it, it will drift for tens of thousands of years before passing within a few light years of another stellar system, and it will not be aimed at that system in any deliberate way. It is not a starship. It is a small probe with a plutonium heater and a fading radio, going somewhere that nobody chose except by geometry. But it is proof of something. It is proof that the machines we build can go where our bodies cannot. It is proof that the two definitions of exploration can be separated in practice, and that we have already begun to separate them. And then there is the other end of that same asymmetry. The James Webb Space Telescope, launched at the end of 2021, sits at a point in space about 1.5 million kilometers from Earth, in the direction opposite the Sun. From that position, its enormous gold-coated mirror stares outward at the deep universe. It has, in the years since it began operating, seen galaxies whose light left them more than 13 billion years ago. It has photographed structures at distances so extreme that the light we now receive from them was emitted when the universe itself was only a small fraction of its current age. No crewed spacecraft will ever visit any of those places. Not because of a wall in space, but because of the mismatch we have been talking about from the beginning. The tools we have for crossing cosmic distances are, at best, capable of putting a small crew somewhere in our own stellar backyard. Everything past that boundary belongs to the telescopes and the light they gather. And yet, in another sense, humanity is already there. We have already seen galaxies no crew will ever visit. We have already mapped the atmospheres of planets we cannot reach. We have already listened to the whisper of the cosmic background radiation, which encodes the state of the universe less than 500,000 years after it began. The reach of our vision in every direction is now measured in billions of light years. The reach of our bodies is measured in a few light seconds. We can see far past the distance we can survive. We have been able to for a long time. This is what the question we started with really means. Once you have followed it all the way to the end. It does not mean that space has an invisible boundary that kills every human being who crosses it. It means that beyond a certain distance, the journey stops being something a single human traveler can complete, and starts being something a species can only accomplish by other means, by machines, by descendants, by instruments, by imagination. The distance no one can survive is not a coordinate in space. It is the point at which distance in space stops being possible to translate into a survivable amount of time. And here is what I think is genuinely worth sitting with at the end of this. For most of human history, exploration meant that a person went somewhere, experienced it, and either came back to describe it or died trying. The explorer and the arrival were the same event. Magellan's ships made it around the world without Magellan himself, but the men who returned had personally done the thing. The Apollo astronauts walked on the moon and came home to describe it. In every case up to now, the person who arrived and the person who left were, in the strong sense, the same human being. The universe is telling us, quietly but clearly, that this deal does not extend forever. There are places we can reach. Our machines are already going there. Voyager has already crossed a distance no crewed mission has ever attempted. And the machines that will follow it in the coming centuries will go farther still. There are places our descendants may one day live. If humanity chooses to build generation ships, or perfect suspended animation, or extends its lifespan by centuries, then people will one day be born on board vehicles crossing between stars, and other people will one day step off those vehicles onto planetary surfaces around suns that are not our own. They will not be, in the biological sense, the same people who left Earth, but they will be the continuation of a story that Earth began. And there are places our telescopes have already seen that no human being ever will physically visit. Galaxies whose light has been traveling since before the solar system existed. Regions of the cosmos so distant that even at the speed of light, the round trip is longer than the current age of the universe. These places are real. They contain real stars and real worlds. They are within our line of sight. They're not within our reach. The universe, in other words, is not one thing to humanity. It is three things. It is the neighborhood we can inhabit, which extends generously to the outer edges of the solar system. It is the wider region we can send machines to. And it is the enormous, breathtaking, mostly unreachable rest of it, which we can see and study and understand without ever standing on it. The distance no one can survive is the boundary between the first two zones and the third. It is where exploration in the old sense, a person going somewhere and coming back, gives way to exploration in the new sense, sending, watching, building things that will outlast us, trusting that the story continues after the individual stops. Some people find this depressing. I do not. The old idea of exploration was always going to run out. It was tied to a particular scale. The scale of a single life. As long as the destinations were on a human-sized planet, that scale worked. Continents could be crossed, oceans could be sailed. Even the moon, in the end, was close enough. Every one of those journeys fit inside a human lifetime, because Earth is small enough that it does. But we do not live on Earth alone anymore. Not really. The moment we started building telescopes, we began to inhabit a much larger universe, one in which the destinations are not on the scale of our lives. They are on the scale of galaxies and stellar populations and cosmic time, and that scale was never going to let a single person walk across it. Not because the person was inadequate, because the universe is huge in ways that are not negotiable. What we are discovering at the end of this walk from Earth to the outer dark is that our species is bigger than any individual member of it. We can collectively know things that no individual will ever see. We can collectively reach things that no individual will ever touch. We can collectively be a presence in a universe whose full extent no single human can ever survive to cross. That is not a failure of exploration. It is a change in what exploration is. For most of history, exploration was a personal act. A voyage undertaken by a person, completed by that person, remembered by that person. Beyond a certain distance in space, exploration stops being that. It becomes an inheritance, something one generation begins, and another generation continues, and a third generation completes, and a fourth generation learns from. Something a species does over cosmic time, not something a person does over a single life. Voyager will still be moving through interstellar space long after everyone alive today is dead. That is not a tragedy. That is what it means to send a probe into deep space. The people who built it accepted, when they aimed it, that it would outlive them. That was part of the point. They were not going with it. They were sending it on behalf of a species that would continue existing after they were gone. When it finally passes near another star, tens of thousands of years from now, there will be, if humanity is still here, some descendants of the people who launched it, still telling the story of the small machine that left the solar system when they were young. That is the shape of the answer. There is a distance in space no one can survive. That distance is not fixed. It moves with the speed of our ships, and the length of our lives, and the ingenuity of our engineering. For any plausible technology, it lies somewhere out past the solar system, somewhere before the nearest stars. For any individual human crew leaving Earth today, it may lie much closer than that. Perhaps somewhere between the orbit of Mars and the outer planets, where accumulated damage and lost rescue and finite supplies quietly conspire to make an original crew's round trip unlikely to succeed. Beyond that horizon, missions do not become impossible. They become something else. They become one way. They become multi-generational. They become robotic. They become inheritances. Things one century of humans begins on behalf of another. The individuals who leave Earth are not the individuals who arrive. Sometimes, no individuals arrive at all, and only a machine does. Sometimes, not even a machine can go. And only our telescopes reach the destination, gathering light that was old before we were born. The universe contains places our machines will eventually reach. It contains places our descendants may one day inhabit. And it contains places our telescopes have already photographed that no individual human being who leaves Earth will ever survive long enough to see with their own eyes. That last category is the largest of the three, by an enormous margin. Most of what is out there is in it. Most of what we know exists is in it. Most of what our species will ever learn about the cosmos will come from places no member of our species will ever personally stand on. That should not make you sad. That should tell you something about what it means to be part of a species that can, with its instruments and its patience, know a universe that its bodies cannot cross. Somewhere between the orbit of Mars and the light of Proxima Centauri, distance stops being a length and becomes a lifespan. Beyond that point, exploration is no longer a voyage. It is an inheritance. The people who leave are not the people who arrive. The machines can go where the bodies cannot. The telescopes can see what the machines cannot reach. And the universe, for all its indifference to any of this, continues to sit exactly where it is, waiting. Just very, very large and very, very old, and mostly beyond the reach of any single life that ever begins on this small blue world we happen to have started from. There is a distance in space no one can survive. It is not measured in kilometers. It is measured in the mismatch between how far we can see and how long we get to live. And the honest, quiet gift of understanding, that mismatch is this. We do not have to survive every place we know about. We only have to be the kind of species that keeps looking outward anyway, that keeps sending things, keeps building things, keeps leaving marks on the dark that will outlast us, trusting that the story continues in some form after we are gone. That is not the end of exploration. That is what exploration finally becomes.